right here. Bolersev and Taylor have proposed gaining greater parsimony. So you know that parsimony is a concept where you want to explain a lot with less. Yes?
Yes.
And they have suggested a generalization of the GARCH model. So that's what we call the generalized autoregressive conditional heterocelasticity model. And the conditional variants are given as this follows, right? We have the variance of the residuals right here. We have the arch term right here of Q order, but we also are going to include the variance of past periods of times right here. Yes, and that's why it's called the generalization. So the generalized terms are given just from this part, and this part right here, it's the autoregressive conditional heterocelasticity, right? So what is the model looking for? The model is looking for to explain the variance over time by two parts, or explain it by two parts. The first part is the conditional heterocelasticity that we're modeling using the square terms of the residuals in the past periods of times. And the second part of the model is seeking to explain the variance of the model given the past values of such variance. Yes. So this is part of the generalization in this case, and this one would be the arch structure right here. Yes. So in this case, the model is defined as a GARCH with Q order in the arch terms and with N order in the generalized part, that is, the variance of the past periods of times. It includes the past values of the variance as well, given right here. And we're not only using the square terms of the residuals, which is the original arch model. We need to ensure something that gives the validity of the model. Yes, and consider that this model, the model that we have stated, is only valid if the above condition is satisfied. Yes. So what is this condition right here? This condition right here is going to take the estimators right here, the estimators of the arch part of the model and the estimators of the variance part of the model, that is the generalized part. And the sum of these estimators right here, it should be lesser than 1. Yes, because if it's not lesser than 1, the sum of this, it means that the variance of the model, which is what we're trying to explain right here, it's become explosive if it's bigger than 1, for example. That means the variance is not converging to a steady point. So the variance is becoming explosive. Maybe you have seen already what happens when an autoregressive structure has a coefficient bigger than 1. Yes? Let's say this is the time, and let's see this is one X series. And let's see, we fitted a model where we're going to estimate the present value of X, giving an autoregressive part in xt minus 1. Yes? And then let's see, it has an estimator associated. If beta, in this case, is bigger than 1, the process of the autoregressive is becoming explosive. That means it's getting unstable. Yes? The same idea applies to this case, right? Because if the variance of the model computed by the GARCH model, that is the generalized autoregressive conditional heterocelasticity, regarding to the sum of the coefficients, is not lesser than 1, we have an explosive variance. That means that volatility becomes unstable, and highly unstable, we can actually just understand what is happening. So the model becomes invalid if such sum of coefficients in this part is greater than 1. Is it clear?
Yes. It's clear.
All right. In that case, where the coefficients are greater than 1, then we have a non-existing unconditional variance. So the problem is we cannot model the variance if that happens, or we have to change our model, maybe include a bigger order of the arch terms, or maybe of the generalized terms. Maybe that would be some of the solutions. Now, I want to introduce you some of the vector notations. If you desire, maybe we can skip this out.
Yeah, we can skip.
All right. So, how we are actually connecting the first model, which is with what we stated in the first time, which is the autoregressive model, with the GARCH model, right? So this is called, most of the times, the mean equation, yes? And the mean equation is going to give us the expected value of the dependent variable, but we also want to consider the error structure regarding to the volatility, which is has. So we connect the GARCH model with the mean equation, that is the equation right here. We connect it by defining the structure of the error term. And we have that structure given by this product. First, we have a random walk process, which is also called a white noise process. In the original GARCH model, this white noise process right here is assumed to be normally distributed with zero mean and a constant variance. And we multiply that white noise process by a standard deviation. Yes? And where it comes from, this standard deviation? This standard deviation is the square root of the volatility that we're modeling with the ARCH model. Yes? So this is how we link the GARCH model with any of the models actually. This could be maybe a moving average model. This could be, I don't know, another kind of model like a multivariate framework structure model and so on, right? But the important thing is that we're linking these mean equations of the general model we have stated through the residuals. And the residuals are going to model the volatility, which is present on the data. Yes? Because in this case, we're assuming that our first model given by this, the mean equation model, has a property in the residuals which is called heteroelasticity. And we're making some conditions of that heteroelasticity when we're going to structure this residuals, right? Some other models may not have this assumption of the distribution, right? So for example, this would be another distribution. It could be a non-normal distribution. It could be a student distribution, binomial distribution, etc. Yes, but this is the usual assumption that we're modeling that the unobserved part that we can control, that is given by this term, is assumed to have a normal distribution. And now we start modeling what it refers to the volatility. Yes, that is the main idea of these models.